So today we're going to be covering the 6 trig functions. Okay, so those would be sine, cosine, tangent, secant, cosecant, and cotangent. Okay, those are the 6. Now, in order to understand these 6, we are going to do so in the fashion of radians. Okay, so usually sine and cosine are related to the angle measure of triangles, and those angle measures are going to be in degrees. But for when we understand them graphically, we're going to understand them in the context of a new unit, radians. So if you're unfamiliar with sine, cosine, and tangent and how they use degrees to measure triangles, then I highly recommend you go check out the triangles and trigonometry video we have about finding angles in right triangles and about finding side lengths and using the trigonometric functions. Today we're only going to consider how they behave graphically. So for those of you who have never heard of a radian before, so a radian is like an angle measure, but instead of being a measure of angle, it's a measure of distance, okay? We're going to get more in depth in that on our unit circle video, but that's unnecessary knowledge right now. Just know that radians is another way of expressing angle measure, okay? So the way we convert between these two is that 180 times your radian value divided by pi equals your angle value. And in the same sense, your angle value divided by 180 times pi equals your radian value. So if there are 360 degrees in a circle, that therefore means by this equation that there is 2 pi radians in a circle. Okay, and we are going to be interpreting with respect to this. Let's first start with the graphs of the trigonometric functions. Now I'm going to put on my x-axis my values in radians. Pi over 2, pi, 3 pi over 2, and let me extend this out a little bit, 2 pi. So 2 pi is my 360 degrees. It's my one complete revolution. Okay? So the sine function, this is going to be f of x equals sine x, is going to start at the origin, and it's going to start going up until it reaches pi over 2, at which point it's going to start going down until it reaches pi, which in turn it is 0 again. Then it's going to continue going down again. It's going to reach a minimum at 3 pi over 2, and it's going to continue coming up until it is 0 again at 2 pi. So this is the sine function. Notice how at the beginning we start at 0 and the function is going this way, and at 2 pi we start at 0 and the function is going this way. So in 2 pi radians we have completed one full oscillation or pattern through the sine function. Now next to that, let's consider the cosine function. The cosine function, very similar to the sine function. We're going to graph f of x equals cosine x, of course with x being in radians. So the difference in the cosine function is it starts at the maximum value. The maximum value for the sine and cosine functions is 1. Okay, it starts at the maximum value, and now it starts to go downward. It encounters 0 at pi over 2, and then it goes down to its minimum value. The minimum value for both the sine and cosine functions being -1. Okay? It's going to encounter its minimum value of -1 down here at pi, and then it's going to come back up, reach 0 at 3 pi over 2, and then reach its maximum value of 1 at 2 pi again, and you see we have completed one full loop. Now from here on out, it's going to continue oscillating exactly the same way it has been oscillating up until this point, and that is a unique characteristic of the cosine and sine functions. They oscillate back and forth to infinity forever in both directions. You can draw the extension of the sine function on the negative section as well. Okay, and like I said before, max value of 1, minimum value of -1. Now, moving on from there, we have our composite trig function, which is going to be the tangent function. Okay? Y equals tan x. Now, tan, if we remember, is equal to sine x over cosine x. So therefore, tangent x is going to have vertical asymptotes whenever cosine x is 0. So I am again going to draw my pi over 2, my pi, my 3 pi over 2, and my 2 pi. Okay? The tangent function looks a little something like this. Where it has vertical asymptotes wherever cosine theta is 0. Okay? And since it is technically a rational function, it is going to diverge to negative infinity on this side and positive infinity on that side. Okay? And we also notice here that the tangent function repeats at a much faster rate. It repeats every pi radians, whereas the previous function repeated every 2 pi radians. Something to keep in mind. You can see here that if we overlap tan x with cosine x up top, you see that cosine x, 0 at pi over 2, and here, asymptote pi over 2. Next, let's move on to probably something that's new for a lot of us. F of x equals cosecant x. What is cosecant x? It equals 1 over sine x. So pretty simple now. Okay, let's draw a graph of it. All right, we're going to start 2 pi, and keep in mind that all of these drawings can be extended to infinity in both directions. Please don't lose sight of that. Okay, let me start with pi over 2, then pi, then 3 pi over 2, then 2 pi. The cosecant function descends down from infinity, encounters pi over 2, and then ascends back upwards to infinity, forming an asymptote here at pi and at 0. Okay? Now, after that asymptote, you will notice that the cosecant function reappears out from negative infinity, comes back up, touches 3 pi over 2 like this, and then descends back down to negative infinity, forming a vertical asymptote at 2 pi. Okay? You may ask yourself the question, why does it stop before it reaches the x-axis? Well, it stops whenever it hits the value 1. Because the maximum value of sine x is 1, the most the denominator could ever be is 1. So our cosecant function will never evaluate to anything less than 1. Or in the case when sine x is negative, never be less than negative 1. So this area right here is sort of a gray area that the cosecant function can never enter. However, if we graph sine x on top of it, you will notice a pretty peculiar pattern. That wherever sine x goes, this thing gently touches it. That would be f of x equals sine x. Now the next one is going to be f of x equals secant x, which, if you are following the patterns, is 1 over cosine x. Okay? If we draw this guy, let's first mark our x-axis, pi over 2, pi, 3 pi over 2, and let's extend it a little bit, 2 pi. That's closer to here. We're going to start like this, diverging to an asymptote at pi over 2, then coming back up from the ether at pi over 2, descending back down, and then returning back up from infinity to finish out at 2 pi. Okay? Now this looks very similar to the cosecant function. It's just shifted a little bit, the same way how cosine is just a shifted version of sine. Okay? If we draw the dotted lines to represent our asymptotes, you might be able to see that slightly better. Okay? And if I were to continue to graph this, you'll see that the upside down and right side up parabolas do not just cut off there. They simply pursue on to values we did not consider in this graph. And the same way that sine x did, if I were to graph f of x equals cosine x here, I'm going to draw him like this, same way he was on the previous graph. And you can see that cosine x always grazes his brother at the minima and maxima. And now, if we are to graph the f of x equals cotan x function, this is simply 1 over tangent x. And since we know tangent x is sine over cosine, we know this is equal to cosine x over sine x. And the graph of this follows largely the same reasoning. We're going to come up here, descend down, cross over pi over 2, descend back down again, and just continue to asymptote as tan x had originally done. And you see here we can draw in our asymptote lines, and by contrast, cotan x has an asymptote whenever sine x is 0. So if we go up and consult our sine x function, you'll see that it is 0 at pi and is 0 at 2 pi, and we down here have an asymptote at pi and an asymptote at 2 pi and 3 pi and so on and so forth. So I'd like to remind you all that if you ever need extra help, my Discord server is open. It's linked down below. Anyway, enjoy life.